This is Introduction to Electronics is a course that we offer in the second year. As you can see here, 201 refers to the second year, and it's a course which is offered to all the students, whether the students are of electrical or civil or mechanical, even sciences, even economic students have to take this particular course. The time that we have available to us, half an hour or so, it's not enough to go topic by topic into all the details of the course, but let me try and share as to what we try to do in this particular course at a very broad level. Okay, so the first thing is, if you note, as is expected, it's a course on electronics. So one of the objectives of this particular course is to analyze, to help the students learn how to analyze and design electronic circuits, which is obvious. Along with this particular course, there's a lab attached. So whatever students learn during the theory, they can go to the lab and test some of those concepts. So build and test circuits in the laboratory. And the last one, as I said, because it's a course which is given to all the students, it's important for especially mechanical, chemical, civil, all these different engineering disciplines to realize how electrical engineering intersects or is helpful to their discipline. All right, so that's the third goal that is there here. I'll come back. I'll dwell most of my time on this particular part here. These are the topics of the course. Introduction to Electronics is offered at all the universities, but the course that we offer here is, I think, a bit different from what happens at other places. As you can see here, the course has three modules. The first module basically introduces students to the techniques of circuit analysis. All right, so these different techniques that are there, both steady state or DC analysis, as well as transient and sinusoidal analysis. So that's the first part of the first 1/3 of the course here. Roughly, you can see here all these three modules are roughly of the same size, 11 to 13 lectures each. The overall course is 39 lectures. The second module introduces students to devices, semiconductor devices and analog circuits. And the third part of the course deals with the digital circuits here. And as I was saying, it's a sort of a strange course because it has circuits in it, it has analog circuits, devices, digital circuits, everything rolled into one single course. And the reason why we have a course like this is, if you take electrical engineering students, for electrical engineering students, there would be a separate course on devices here, on semiconductor devices, a full course on devices here, a full course on analog circuits, a full course on digital circuits. So for electrical engineering students, they'll go deeper into each one of those things that are there. For other disciplines, students of other disciplines, this is the only course that they take, Introduction to Electronics. And most of them are not going to take a course on devices or digital circuits and all that. So our goal is, it's a little bit difficult because you have to teach to electrical engineering students and you have to teach to non-EE students here. And so one of the first major questions that we have to deal with in a course like this is, it's not a problem in teaching this course to electrical engineering students. They understand. They've come to that discipline and they know they have to learn all these things. The problem is with let's say, a civil engineer. His questions would be, why should I learn all this? Circuit analysis, analog circuits, digital circuits, all of this, why should I learn? A chemical engineering student may have a similar question. Why am I learning all this? So a big problem with this particular course is motivation. If the student feels that this course is irrelevant, he or she will not be motivated to understand the ideas that this particular course presents. So one has to address that. How is this course relevant here? Now, if some of you want, I can share this particular slides with you. So books and all that we typically follow are all here. We have a distributed grading scheme, midterms, final exams, quizzes and all that. So the course has 3 lectures per week, 3 hours of laboratory per week, and 1 hour of tutorial. A tutorial which is basically a problem solving exercise here. So that's how about 7 contact hours are there. Let me come back to the main question that I raise is, how is this course relevant? Now, the students have no difficulties. As all of you know, first year and maybe a part of second year, we teach a lot of science. We teach physics, we teach chemistry, we teach a lot of maths. Students have no difficulty in understanding why are we teaching science. Engineering rests on science. We can cite several examples here. We can take an air conditioner. If you're a mechanical engineer, you're interested in designing an air conditioner, we know that the air conditioner is based on all these different principles of science that are there. If you don't understand these principles, that gases liquefy under pressure, when a liquid vaporizes, it takes heat from the surrounding. And if you don't understand all these scientific principles, then you won't understand the air conditioner. You won't be able to design an air conditioner. So it's very easy to convince them, look, when you come into an engineering discipline, you have to have a good grounding in some of the fundamentals of science. They have no difficulty with that, right? Similarly, students have no difficulty in understanding why they're taking again a course in calculus, a course on matrices and partial differential equations, because we know that almost all the engineering problems that we handle, we transform it into a mathematical problem, right? Even in electrical engineering, for example, if I look at a diode, I understand diode through a mathematical equation, equation which relates current to voltage. If I take a circuit, very simple circuit consisting of a diode and a resistor, I understand it again, we transform it into a nonlinear equation. We have to solve this equation in order to understand how this particular circuit works. So no matter which engineering problem we take, we transform it into a mathematical problem through the process of modeling. And therefore, maths is very important, which students also obviously appreciate, that I have to have a good understanding, good grounding in the different disciplines of mathematics. The issue arises, why electronics? Why should I learn electronics? Is it as important as maths and science that we are talking about? Because we introduce it, this was a course that at one time we used to offer to all the students in the first semester. The students who just would come in after clearing the JEE, first semester this course would be offered. Later on, because the students didn't have all the mathematical concepts that were required, we shifted it to the second year. But the issue is, why should all the students take it? Is it as important as science? Is it as important as maths? So that's the question that I think we need to address, so that these students are properly motivated. And the way, so this is a point that I would like to address before I go on to more details here. Why do we require all the students to take electronics? Is it as important as maths and science? And the thing is, the way, it's very easy for anybody at least to appreciate that electronics is very important, right? So, I mean, all of us can point out to innumerable examples, all of which have electronics, if not the central part, electronics embedded in them, right? So it's very easy to point out, look, electronics has transformed modern life. So that's not the issue. The issue is, how can electronics help a mechanical engineer? How can a civil engineer benefit from electronics, right? So the way, at least I like to point this out to the students is basically on the basis of two sentences, two statements. One is that no matter what, as an engineer, whatever you're trying to do, right? Every action requires, everything that you try to do requires energy. Wherever you intervene, whatever you try to do, it's an obvious self-evident statement that it requires energy. Nobody has any argument with that. The second statement is, electricity is a very useful form of energy. Why? That is important because electricity, as all of you know, is not directly useful to us. Our direct contact with electricity is painful, right? We get a shock. The electricity is useful for different reasons, and that is, the first reason is, of course, that it can be converted into other forms of energy. You can convert it into heat, light, mechanical motion, or whatever. It's easily converted back and forth, right? Chemical energy, all of these things you can do. The most important point which electronics does is that it can be precisely controlled. That this is a form of energy which I can very, very precisely control. There's no other form of energy, let me make a statement, which can be as well controlled as electricity. So it's a form of energy which I can precisely control. What does it mean, control? It means that I can make it do whatever I want. When I can control something, I can manipulate something, I can force it to do what I want it to do. Of course, there are constraints, there are limitations. So this then brings us to the following. Electronics, if you look at the first two sentences, every action requires energy, and electricity is a very useful form of energy, precisely controlled and easily converted. So what I'm saying is, no matter what you're trying to do, if you're facing a problem, if things are not as easy to do, convert it into electricity, into an electrical signal. Once you convert it into an electrical signal, as I said, now you can precisely control it. It's very easy to do processing in the electrical domain. After you do that, convert it back into the form of energy that you're interested in. And then you've obtained a system which is much better than the original system here. So this is what I'm trying to do. I'm trying to say that in your environment, whatever you're trying to do in your environment, if let's say it's not very convenient, whatever you're trying to do, build a system, solve a problem, it's not very convenient, what you do is you take whatever inputs you have, using a sensor, you convert it into an electrical signal. Do all your processing here. And as I said, you're not really interested in electricity per se. So after that, you convert it back into the signal that you want. Through an actuator, you convert it back. And then you're back into intervening into the environment. Very simple example is, let's say I'm trying to communicate in this particular room. So my interest is in the audio signal, and I want my audio signal to be heard at the back of the room also, and I'm not able to reach to the back of the room. So obviously, I take an audio signal. A direct communication of audio signal from this point to that point is becoming difficult. So I take the audio signal. All of you know this. Take a microphone, convert it into an electrical signal, do the processing. Processing can be very simple. Simple amplification could be far more. You could do noise reductions. You could do all kinds of things here. You could even record and keep a copy. All kinds of things you can do. But convert it back into an electrical. So electrical signal comes out here. Use a loudspeaker. You're back to an audio signal. So your interest is in audio signal, but directly handling audio signal, that form of energy is making things difficult. So what do? You convert it to electrical. You convert it to electrical, do all your processing here, and then back here. So this diagram here, it becomes a central organizing theme of the course. How is electrical engineering benefiting? And there are numerous examples. So what we are saying is, look, you're designing a mechanical system or a chemical system, right? What you do is, you will benefit if you take some of your inputs, some of your signals, convert it into an electrical signal. Do your processing, and then convert it back into whatever you're interested in. And thereby, you have a system which is a much better system than a pure mechanical system or a pure chemical system. You have a better system available to you, right? And each one of us can find numerous examples of how this is being done. For the mechanical engineers, for example, a nice example is an anti-lock braking system. Traditional braking of a car or whatever is a mechanical hydraulic system or whatever it is, right? But in this case, for example, if you add electronics to it, then you mount sensors on each one of those wheels. You can monitor what is the rate at which the wheels are rotating, and based on any difference in speed, then you can apply more pressure to one wheel or the other. So you can have an intelligent braking system, an anti-lock braking system, basically by adding an electrical subsystem to your braking part here, right? So we can find numerous examples which highlight how we can add an electrical system and to add to whatever system one is really interested in, mechanical, chemical, or whatever it is. And as I said, there are many examples that we can cite. Smart buildings, we can cite examples from the health side, and a lot of other things that are there. The other thing is, what we can do is, so while we are teaching electronics, we can expand this particular electronics part here. See, as I said, carrying out processing of a signal or information in electrical domain is far more easy because we can very precisely control electricity. Now, once you take a signal from the environment and convert it into an electrical signal, typically the signal that you get is an analog signal. Analog signal which is continuous in time domain and in amplitude domain. Now, analog signals are a little bit hard to process. You can amplify an analog signal, fine. If you want to do a integration on that analog signal, you can, many of you may be familiar, you can build an integrator You can build a differentiator. Maybe you can multiply two analog signals, but it's not very easy multiplying two analog signals. If you want to divide two analog signals, if you want to take a log of a signal, or if you want to solve a differential equation, pretty soon you find things become difficult, right? And that's where the other power of electronics comes in, which basically is that you convert the signal into digital domain, right? So you take your analog signal that comes in, you do some analog signal processing, take an A to D converter, and you convert it into a digital signal. Now the real power of electronics has come about. Any product that you look at, modern product that you look at, the real power of electronics has come about because of digital signal processing. Once you go into the digital domain, the processing becomes much easier. The number of transistors and all that you can integrate and build a complex circuitry that's far more complex than what you can do in the analog domain. So the real power of electronics has come because of the digital signal processing here. And of course, you may not be interested in digital signals, so you take a D to A converter, convert it back, and then you do some analog signal processing, maybe more amplification, and then you're back into the environment. So this part here, as I said, this can serve as the organizing diagram of your course. That when I'm teaching different things that are there in that particular course, how they fit into this particular block diagram. When I'm teaching, for example, an amplifier, well, I'm dealing with this analog signal processing. When I'm dealing with digital circuits, gates, and all that, I'm dealing with this particular part here. So this diagram could be a central diagram of this particular course, which integrates and knits together all the topics that are there. The other point which is very important is this digital signal processing here. So processing of digital signals. As I said, this is the reason why electronics has had such a large impact, the processing of signals in the digital domain. And one of the most important aspects of it is that this circuit that we have, digital circuit, is a programmable digital circuit. See, let's say you're trying to do something, and then whatever you're trying to do, if you have to rig up a circuit specifically to that particular problem, that's what typically we do, but that's not as convenient. For every problem, if you have to rig up a very unique circuit to solve that particular problem, makes it a difficult thing. That's where the programmable digital hardware comes in, a microprocessor or a microcontroller, that you have a general purpose digital circuit. And then on top of it, you add a software. You program the digital hardware, and then you make it do whatever you want. So that brings in the role of the programmable hardware is extremely important, and this is what is leading to a hardware software kind of a solution that one is offering. No matter what system, as I said, if you take your washing machine, there would be electronics in the form of microcontrollers, and then in the microcontrollers there would be sitting a code, some kind of a software which would be sitting and controlling different functions and all that. So how does software come into picture? It's something that we can, as I said, remember this is a course that we give to non-EE engineers. So I think they need to see the big picture. What is this? How is this electronics enabling all these different things that are happening there? How does software come into picture? So it's not easy, but if we can show through this introductory course how a programmable digital circuit comes about. We teach gates, fine, we teach counters, and we teach all of these things. But in a very simple way, if we can get them to see how a digital circuit becomes programmable. That is, maybe a very simple set of instructions that are there, and then you can express yourself, any problem that you have, you can express yourself in terms of those elementary instructions. If that can be brought in, then the student begins to see, where does the software emerge? And the software, what kind of a platform does the software run? Okay. So as I said, this is the central organizing part of our part of this particular course, and different things that you teach, if you can plug in and show how it's illustrating how this particular signal flow is occurring, then that would make the course. Otherwise, many times we teach lots of things and they remain disconnected. They remain disconnected in the mind of a student. And what happens is all the different details that you will teach, after a semester or a year, the student is going to forget. Because, they will not encounter those things here. But the big picture, that is what is important that they carry. how can electronics benefit? How can I derive benefit from electronics? Right? So if they carry this particular picture, maybe when they're designing a mechanical system, they're designing something else, maybe they'll think, well, maybe here is where I can convert it into an electrical signal. And then I can talk to an electrical engineer who's a friend, and then he can do all this processing. And then we convert it back into the signal of interest. And therefore, I can do things which is much better than working purely in that. So as I said, this is the block diagram. Then coming back to each one of these things, so that's one part, the big organizing principle of this particular course. The other thing is, at this stage, at least in my experience, we see two kinds of students. One set of students that I find are, you teach them maths, you teach them abstract concepts and all that, and they're very happy. Equations and all that, they don't complain. There are other type of students who constantly want, how is it related to reality? They want, connection to something more concrete. Abstract symbols and equations and all that, they get, after a while they start getting very jittery. Show me how these are related. So the other thing is examples. This how do we connect, all these simple things that we teach to important examples from everyday life. And I'll just, and all these examples are actually sitting there. If we make some effort, we'll find that for each one of those topics, there are beautiful examples. Let me highlight that. Take the case of a simple RC circuit, a circuit consisting of resistor and a capacitor, right? We teach that particular circuit, teach that concept associated with it. If I go and look at an RC circuit, there are two very nice examples which are sitting there, which illustrate the usefulness of an RC circuit. One is a DRAM. Dynamic RAM, everybody is using, my cell phone has 4 GB RAM and laptop has 8 GB RAM. Everybody is talking about these RAMs, right? Everybody wants a lot of memory. These memories are DRAMs, dynamic RAM. And then if we go inside the dynamic RAM, what you find is that how do I get a memory? The memory is a basic simple capacitor. So when I'm talking about a capacitor, fine, capacitor is dq by dv and I equal to c dv by dt and all that we talk about. But a very important point is, look, the capacitor is a memory element. In all your cell phones and laptops and all that, one of the basic memory element is the capacitor. And this capacitor that you see here along with the transistor, this basically acts as a single 1-bit memory cell. And if I want to understand this 1-bit memory cell, this 1 bit is called a dynamic RAM because it has to be refreshed. If you don't refresh it, the capacitor loses its charge. These transistors are, they are not perfect transistors, they leak charge. So you have to refresh it. How often do I need to refresh before I lose the memory? So it basically translates into the transistor can be modeled as an RC circuit, and then how often do I have to recharge? Then basically RC time constants and all that are useful to come up to an idea of how often do I refresh my dynamic RAM. So that's one example that we can begin to talk about in terms of the application of a capacitor, the application of an RC circuit. The other example is this laptop, this LCD screen here that you see here. The LCD screen, if you go and look at it, the LCD screen is also like this. It's like a dynamic RAM. Except that this capacitor that you see here, there is a LCD liquid crystal cell. It's also like a capacitor. It's a liquid crystal cell which you can make it opaque or transparent depending on the voltage that you apply. And along with this liquid crystal cell, there is a transistor sitting in this particular laptop also. A amorphous silicon or a polysilicon transistor sitting there. So this display that we are talking about, LCD display that everybody sees, in cell phones, laptops, TVs, everywhere. LCD display is also like a transistor and a capacitor that is there. And some of the properties of LCD display we can also understand through this simple RC circuit. So my point is, if we can take some of the very simple concepts, RC circuits and other things, and connect it to everyday life. Example is a DRAM, example is a LCD display. And similarly from other disciplines, other areas, other things that are there, we can find very nice examples. For example, if I take an inductor, if I can take an inductor and connect it to now the problem of an RFID or an NFC. Everybody in their cell phone has NFC, near field communication. And we show them how an inductor plays an important role. What role does an inductor? Or we are now increasingly talking about wireless charging. Right? All these are based on basically inductors. And so the thing is not to We cannot go into any of these applications in detail, obviously, but then if we can bring in these applications from things that they're hearing about and connect it to the concepts that we are teaching, it will make the course more interesting. So that's the other point that I wanted to highlight. The other thing is electrical engineering, besides the fact that you can convert your signal into electrical and benefit from it, every subject, so electrical engineering, like any other subject, has very nice concepts in it. Concepts which are not just useful for electrical engineers, but if you look at it in a more general form, is useful to all engineering disciplines. It all depends on with what perspective you look at it. Let me show you a familiar, from those who are from electrical engineering would remember a Thevenin's theorem. Thevenin's theorem, for example, right? So here is a circuit. For those of you who don't remember, let me just tell you what it is. So there's a circuit that you want to analyze. And this circuit has, as you can see here, 3 meshes. This is one mesh, there's another mesh, and 3 meshes. So it's a 3-mesh circuit. And you want to analyze this particular circuit, right? One of the ways in which we do is we use a theorem called Thevenin's theorem. And what we do is, let's say we build a Thevenin's equivalent at this particular point. I break the circuit here and I build a Thevenin's equivalent. And when we build the Thevenin's equivalent, what we need to do is find out what is the open circuit voltage here. This is this particular part. What is the equivalent resistance looking of this particular circuit, which is here. And then you put both these blocks together and you construct the circuit that you need to solve. So a 3-mesh circuit eventually translates into 1 mesh, 2 mesh, and a 1 mesh. Fine. What happens is people, when we teach, the students get all bogged down into Thevenin's theorem. How do I find the open circuit voltage? How do I find the resistance? And how do I put it together? In the details of it. But the important point here is the following. You have a more complicated problem, a 3-mesh problem. And what are we trying to do? When you take a more complicated problem, what do we do as an engineers? We decompose it. We break it up into 2, 3 simpler problems. That's what we are trying to do. A 3-mesh problem has been broken into a 1 mesh, a 2 mesh, and a 1 mesh. So you have to, instead of solving one problem, which is of complexity 3 mesh problem, what you're doing is you're solving 3 problems, but of lower complexity, 1 mesh, 2 mesh, and 1 mesh. So you have decomposed it into 2. If you want, you can decompose it further. So eventually, what we are doing is a 3-mesh problem is reduced to a solving only one single mesh problem. So one can look upon Thevenin's theorem. Is Thevenin's theorem simplifies circuit analysis by reducing number of meshes in the circuit by 1. It's a very different perspective that you won't see. But this is more generalizable. More generalizable in the sense that Thevenin's theorem maybe you cannot directly apply to a mechanical system. But the principle behind this is what? Taking a system, breaking it up into simpler systems. And then taking that simpler system, if you're finding it difficult to do, break it up into further. So this hierarchical decomposition of a complex system into simpler and simpler system is a very general engineering principle. In electrical engineering, we are applying it in the form of Thevenin's theorem. In some other system, some other place, we may be applying it in another form. It also brings us, this electrical engineering, this particular topic also offers us another interesting, one can engage students in a debate in the following sense. Take the circuit, for example. The circuit, I can transform the circuit into a set of equations. I can transform it into a set of equations, and these equations, then one can write a simple algorithm. Circuit simulators are there, which will give you the values. So the questions that many times we engage our students with, well, we are asking you to analyze this particular circuit, right? The same circuit, a circuit simulator or computer program can solve it much more accurately and in much less time than what you can do. So what is your role? What is the role of a student? If the computer can analyze that particular circuit faster without any error and with much more precision, what is the role of a human here? Now, this is very important because there's a lot of debate now. Increasingly, automation is occurring. What is the role of humans? What are we going to do in future? We can engage the students in this particular debate, let's say, through these simple examples. Now, many students, they tell us, yes, the computer can give me a numbers, solve this particular circuit and tell me a 1 ampere current is flowing through this particular resistor. But I can derive an expression. I can derive an expression. From a circuit simulator, I don't get an expression. But many of them are not familiar that there are programs that are called symbolic circuit simulators. If you go and search internet, you'll find some free programs also, symbolic circuit simulators. So then I show them, well, look, this program is there, and it can give you an expression also. Then they're in a little bit trouble. Well, the computer is giving me an expression also. Then they say, well, maybe I can simplify it. I can get a simpler expression. The computer cannot simplify it. It gives me a long expression. Then, interestingly, into that program, you can say, I want an expression which is within 10% accurate. You can feed in the kind of accuracy that you want. And the program simplifies it also. So now you get a simpler expression also. So then the issue is, well, the computer is giving me an expression also, a simple expression also. Why am I doing all this? What is my role into it? And then that brings in is that the central role is not just number crunching, getting a number, but the central role is understanding. That you have to understand. The role is not simply get 1 ampere or 2 ampere here and there. The role is to understand. Once you understand, your role would be to come up with a new circuit. Without understanding, you will not be able to modify and come up with new circuits, right? And in this context, look at the role here. If I use let's say, a computer-like approach to analyzing circuits, right? Versus a more human-like approach. Look at the differences. I just showed you Thevenin's theorem. Thevenin's theorem, if I apply to this particular circuit, I will get an output voltage which is like this here. Some complicated expression that you see. Okay? V0 in terms of these different elements here. Look at this expression and look at an expression if I were to do it more computer-like. Computer-like means take this particular equation, write it into a set of mathematical equations and eliminate all the variables and get it. I will get an equation like this. 2 equations are being given to you. One equation here and the other here. Can you see the difference between the two? Both will give you, if I plug in the values, both give you the same value of V0. But there's a big difference between the two. This expression, we call it a structured expression. And this has no structure in it. Absolutely no structure. This expression tells you, for example, looking at this expression, one can tell how important is R1. If I find R1 is 1 kilo ohm and R2 is 100 kilo ohm, then I know R2 is not really important. R2 parallel R1, 100K parallel in 1K, R2 is not important. From this expression, I cannot tell anything. So here is an expression which will give you a number. And this expression will also give you a number. But where do they differ? They differ in terms of understanding. I can get a lot more understanding through the first expression, and I can't get much understanding through the second expression. That's where the difference between the two. So my point is that at many of these places, the simple concepts that are there, we can use it to illustrate and engage students in important debates over the role of automation. For example, through circuits, through these very simple examples. The point that I was trying to highlight is the importance is not analysis, number crunching, all of that should be de-emphasized. They are a means. They are a means to an end, and the end is understanding. Understanding what this particular circuit is doing. Similarly, as I'll wind up, there are other many interesting examples. For example, when we look at sinusoidal steady state, this is something that we routinely do in circuits. When we have a sinusoidal signal and we have various elements, the analysis of circuits involves sinusoids. Adding and subtracting sinusoids is not easy. And so what we do is we use the concept of phasors. Now, again, as I said, most of the time we get bogged down into doing all these phasor analysis, calculating currents and voltage. But what is the larger theme here? The larger theme is addition and subtraction of sinusoids directly is not very convenient. It's difficult. What you do is you take sinusoidal variables, convert it into complex variable, do all your complex algebra, convert it back into a sinusoid. If you recall, it's the same theme that we said if something is difficult in one domain, you convert it into electrical domain. Now we are saying in electrical domain, if something is difficult with sinusoidal variables, you convert it into another domain, which is the complex domain. And you solve problem there, and then you transform it back into sinusoid domain. So this general theme of transformation If things are not easy in one domain, convert it into another domain. Do everything there, convert it back. And then you have a better system here. The last one that I want to highlight, as I said, each one of these examples you can take to illustrate some larger engineering themes, larger issues, which are important and which maybe students would remember, 1 year, year and a half, whatever down the line. Nitty-gritty details they'll forget. So it's important that we talk about it. Take amplifiers, for example. The details again are not important. Take common emitter amplifier. The common emitter amplifier, even common emitter amplifier is a little bit involved design of this particular amplifier. You have to select proper bias point. You have to think of stability. You have to achieve a certain amount of gain, input resistance, output resistance, bandwidth, all kinds of things that are there. You have to balance all of that in order to design a common emitter amplifier. Now, there are very few people who can design these amplifiers, right? And but a lot of people want amplification. As I said, if everybody wants to take a signal, convert it into electrical signal, and you want to amplify it and do something, everybody wants an amplifier. So now the issue is everybody designing amplifier is difficult. So what is the solution that electrical engineers came up with? So what I'm trying to highlight is the difference between a custom design, a semi-custom design, and a standard design. When using amplifiers as an example, we cover op-amps, we cover common emitter amplifier, but we use that to engage students in 3 different ways in which we do design. Custom design is where you come up with a certain requirements and I design an amplifier specifically to your need, right? That's very hard because, we have very few engineers. It's very expensive that anybody who wants an amplifier and you design an amplifier specific to that particular person, that's very hard. Custom design is not economical. What did the electrical engineers do? Well, they invented this op-amp. Op-amp is a very complex circuit inside. Very, very few people can design an op-amp. It's a very complex circuit. It's an amplifier. But what they added, a crucial thing is, it's a very complex circuit, but it's customizable. That's a very important part. It's customizable in the sense that you can take an op-amp. It has a very simple interface, and you can customize it. So in fact, anybody can take it. A material scientist or whatever can take an op-amp, and what they can do is they can add an R1 and R2, and the ratio decides a gain of the amplifier. Anybody can build an amplifier. A 10th class student can build an amplifier now. But inside this op-amp is a very sophisticated circuit, but with very simple interface. And you can customize it. So this is the important point that one can illustrate through the op-amp here, the customizability, that semi-custom design here. As I said, there are lots of interesting things that are sitting there. And one of the things that sort of motivates me is, I'll leave you with this, is the first line of a poem that you see here, to see a world in a grain of sand. The idea is, the poet is of course saying that if you take a small piece of sand also, and if you examine it thoroughly and with the right perspective, maybe you can see the entire world in it. Of course, that's a poet's imagination. But what we can take from here is that whatever little thing that we are teaching, small things that we're teaching, RC circuit, a common emitter amplifier, or an op-amp, or whatever, each one of those things, if we look at it with a right perspective, illustrates a very large and very important theme. If we can do that, if we can help the student to see that an op-amp is an example of a semi-custom design. The semi-custom design is very general. And in RCs, different things that are there that you see here, that this illustrates a powerful principle of, when you write an expression, you write an expression in a form such that it's a structured expression. It gives insight into what that particular expression means. Okay, so if we can do that, then the course becomes not just a course in electronics, but the students would benefit the course from that particular course over a long period of time. Okay, so let me stop here, and